Hi guys, thank you for attending BOGO's Explore UT presentation. My name is Sean, and today I'm going to take you through some fun experiments in the world of optics. So first, let's ask the question, what does optics mean anyway? Well, the answer to that is basically anything that has to do with the science of light. So with that out of the way, let's jump right into some experiments. The first experiment I have involves sorting gummy bears. There are 3 different categories I can sort my gummy bears into: red, clear, and green. If I take a handful of gummy bears and expose them only to red light, this is what I see. And I'm actually really happy about this because red is my favorite flavor of gummy bear. So I'll take all the red looking ones and push them over here. And then maybe a couple of them look clear to me. But the remaining dark looking ones, they don't really look green, but they definitely don't look red or clear. So I'll move those over to green. And now, if we turn back on the room lights, we can see how I did. And you can see that I actually didn't do that well. Look at how many clear gummy bears ended up with the red ones. Why is that? Why do those 2 colors look so similar under the red flashlight? Well, the red gummy bears look red because they reflect the red light from the flashlight to the camera. That's actually why any red object looks red, because they reflect red light and that's what reaches our eyes. Green gummy bears, on the other hand, only reflect green light. When they're exposed only to red light, they absorb all the light and look dark. That's called absorption. Notice how the green gummy bears almost look black. The color black is special because it doesn't reflect any light. It instead absorbs all colors of light. The color white is special too, but it actually reflects all colors of light. The clear gummy bears transmit light, but the white paper underneath them reflects that light. So when the clear gummy bears here are illuminated by red light, they look red because the white paper underneath them reflects the red light back through them. If I switch to a green flashlight, we can see that the green gummy bears look green, but now it's the red gummy bears that turn dark. Green light is only reflected by green gummy bears. The red gummy bears are absorbing the green light. If I change to a blue light, both the red and the green gummy bears look dark now because both of them are absorbing light. The second experiment I have also involves absorption. Here, I have a group of clear-looking beads, but these are actually very special beads. These absorb ultraviolet light, otherwise known as UV light, and then change color. Let me show you with this UV flashlight. What's happening is a process called fluorescence. When an object absorbs light of one color and then emits light of another color, that's called fluorescence. So these beads are absorbing UV light from the flashlight and then giving off blue, pink, and purple light through fluorescence. UV light from the sun can be harmful for our skin. Sunscreen is designed to block UV light to stop it from reaching your skin. If I coated these beads in sunscreen, they wouldn't be able to absorb UV light, which would prevent them from fluorescing and changing color. The third experiment I have for you demonstrates a property called refraction. Every material that light can pass through has a refractive index associated with it. This describes how well light can move through the material. It doesn't matter if you have one hard material and one soft material. If they have the same refractive index, light will move through them in the same way. To demonstrate this, I have two different jars here. One is filled with water, and the other is filled with oil. I also have two glass rods. If I take one of the rods and dip it into water, you can see the rod's outline clearly. If I take another glass rod and dip it into the oil, it disappears. That means that the glass rod and the oil must have the same refractive index. For the glass rod and water, the light moves through the rod in a different way than it moves through the water, and our eyes can see that. In the oil, however, light passes through both materials in the same way, and they end up looking the same to our eyes. Refraction is important because we can use it for helpful tools. One example is for making the lenses in glasses. Lenses use refraction to change how light hits our eyes. Everybody's eyes are different, so some people need glasses to change how light travels to their eyes in order to see things more clearly. Here, off to the left, I have a third container that's filled with oil. I also have this wooden spoon. Here you can see the normal size of the spoon, but notice that when I dip it into the oil pitcher, the spoon looks much larger. The pitcher of oil is acting like a lens in a pair of glasses because it's changing how we see the wooden spoon. The next experiment I have for you also has to do with lenses, and it also involves laser beams. If I take some laser beams and shine them through this cloudy water, you can see that the beams are traveling straight. But if I put this lens in front of them, the beams now start to bend. This is similar to how the lenses in glasses bend light to help some people see better. While I have the lasers out, there are a couple more things I want to show you. The first is how I can use this water like a mirror. The water here has a high refractive index, and the air above it has a low refractive index. When light is traveling from one medium with a high refractive index to another medium with a lower refractive index, sometimes it can reflect off the meeting point like there is a mirror there. This is an idea called total internal reflection. The other thing I want to talk about is how light has a direction to it. This is a concept called polarization. You may have heard of polarized sunglasses before, and these are designed to block light of a certain direction. Light from laser beams are special because all the light that comes from a laser possesses the same direction. In other words, the light coming from a laser is polarized. If I take my laser beam and shine it through a pair of polarized sunglasses and rotate the laser beam, you can see that the laser light grows weaker and stronger as I rotate it. That's because both the laser light and these sunglasses are polarized. They have to line up at just the right angle for all the light to pass through the glasses. The last experiment I have involves colors of light. I have a special item here called a diffraction grating. You can actually get cool glasses that are made of these called diffraction glasses. If I put the grating in front of the camera, you can see that it breaks up the red light and sends it to different areas. If I change the light bulb to green, you can see that the green light is now sent to different areas than the red light. The same thing is true when I change the light bulb to blue. Now, what do you think will happen when I change the light to purple? You can now see both blue and red light when light passes through the diffraction grating to the camera. That's because you can mix red and blue light together to make purple light. That's what this light bulb is doing to make purple light, and that's also how things like TVs and computers make purple light. What about yellow? Now we can see both red and green light. These are the colors of light that things like this light bulb and TVs mix together to make yellow light. So I have one last test for you. What will happen when we look at white light through the diffraction grating? Now we see red, blue, and green light. Those are the colors of light that this light bulb is combining to make white light. That's because you can make white light by combining all the other colors of light. In fact, even white light from the sun contains all the visible colors of light mixed together.